says good lord. Hydrogen gas and iodine gas react to form hydrogen iodide at an elevated temperature is represented by the following equation. Write the equilibrium expression for this reaction. Okay, a nice little jumping point here. So Kc. Remember that equilibrium constants are products over reactants. Coefficients become exponents. So Hi squared, H2, and I2. Okay, they're all gases, so we're good here. Let's look at the next one here. It says H2 and I2 are added to a previously evacuated container and allowed to react. At a certain time, reaction quotient Q, okay, is 0.67. Following particle diagram is an incomplete representation of the system at this time. The diagram shows the relative number of H2 and I2 molecules, but Hi molecules are not included. Draw the number of Hi molecules needed to complete the diagram so it accurately represents the system. Okay. All right, so what I'm thinking here is that we have an equation for K, which is also the same as the equation for Q, right? Q is just when a system is not at equilibrium. So you got Hi squared, H2 and I2 that's here. And so if I assume that molecules, because we can do molecules and moles the same way, they both represent the relative number of molecules here, I can actually solve for this concentration here. And then I can utilize that information to figure out how many molecules I need to add, right? So if I take 0.67, and I've got 2 molecules of I2, so we put 2 down here at the bottom, and then 3 molecules of H2, basically this becomes x squared, and I can solve for this algebraically. So if I take 6, which is the product of 3 and 2, and I multiply that by 0.67, I end up with 4, so x squared essentially equals 4, so x equals 2. So what I need to do here is I need to add 2 Hi. So Hi shaded in, and Hi shaded in. Just pretend that those are bonded together, okay? But other than that, yeah, it's a straightforward problem. I think maybe some people might just look at the reaction to figure that out, but remember, we're not at equilibrium, so things aren't perfect. Use the value for Q to solve for that, and I think we'll be in good shape here, okay? A student monitors the number of moles of Hi over time, hypothesizes an experimental change that could be applied to a system in a rigid container at time t to result in the change in the number of moles of Hi shown in the graph. So this shows Hi going up. And we assume that the student did not add more Hi to the system. So basically this is a Le Chatelier's principle problem. How can I get Hi to increase? Well, let's scroll back and see here what information we have in the problem. So our delta H is negative, which tells us that this reaction is exothermic. I teach my kids to put heat on the side of the reaction where energy is being added or released. So to get more Hi, you could either do one of 3 things here. And again, I'm not sure what they would expect, but I can either add H2, I can add I2, or what I can do is I can lower the temperature. What I teach my kids is I teach them to relate Le Chatelier's principle to the delta H of the reaction and heat. I tell them to explain it a little bit different way, but this just makes it a little bit easier to explain shifts in equilibrium. So when temperature goes down, so does heat. We treat heat like a reactant or product, so it's just to the right. But what I tell my students is that in a exothermic reaction, decreasing the temperature makes Q no longer equal K. As a result of this, the reaction responds by shifting left or right in order to reestablish equilibrium. This time is going to make more product, or students could say that Q is less than K in order to get the shift to the right, something along those lines, in order to get that information figured out. It really doesn't ask you to explain it. It just says hypothesize this change. So last one, after equilibrium is established, the mixture is transferred to a large container at constant temperature. As a result, with the moles of Hi increase, decrease, or remain the same. So a larger container means that we have a higher volume, and a higher volume means that the pressure is decreased. A decrease in pressure favors the side, according to Le Chatelier's principle. A decrease in pressure favors the side with more moles of gas. But even then, if you didn't know that information, you couldn't tell if it was more or less. Same number of moles on each side, right? 2 and 2 here. So really, there is going to be no change. The number of moles of Hi will remain the same because we have moles of gas equal on each side. So you get a pretty tame Le Chatelier's principle, problem here, pretty tame equilibrium problem. I like the use of the graph, but again, just kind of following some real basic chemistry here in order to be able to solve for some of these more complex problems. Yeah, let's see what the rest of this holds up. We got 2 more questions left.